So how do you get through the loading? Unfortunately, most of it is through codes, through design requirements that are drafted for each type of for generally in each country. Sometimes the codes are determined by the contractor. So, for example, I work on a bridge in India where a contractor is Japanese, and they impose that we use Japanese standards, even though we're in India. So it's really, the design codes are important. Principles are quite similar in all of them, and you need to understand the principles. Sometimes for unusual and larger structures, you do testing, such as wind tunnel test for your wind loading. This is done for cases your codes don't really cover this situation, or you want an extra level of reliability because codes are drafted for general structures and your structures may be quite specific. So the next step, once you've determined the loading, you go for the analysis. It can be done by manual calculations or finite element analysis. It really depends on what you're designing and what level of reliability you want. You have various ways of doing it, which I can't cover in a lot of detail today, but you have a lot of manual methods and various level of deep detail on finite element. And the choice is really yours as a designer of what you use and what level of reliability you want. And then, the different types of materials and different structures require different considerations in analysis. So steel design is all about vibrations and about buckling because they're so slender structures. Concrete is quite complex. You want to make sure it doesn't crack. You rely a little bit more on plasticity, and you can allow some redistribution. For composite structures, it's quite complex because you need to design for both materials, and it becomes a bit of a challenge because you use codes for steel and concrete together. Pre-stress is advanced, and you're talking about a lot of long-term behavior like concrete creep and shrinkage. You also need to think quite carefully about the construction sequence and stressing sequence for your tendons. And for timber is quite complex in the sense that it's very ununiform material. It's an isotropic, and it's often driven by the connection rather than timber body itself. Cable stays are advanced. They're really like a geeky side of engineering. They're very statically determinate and difficult to design. And then you have integral structures, which are increasingly important and popular because of lower maintenance requirements, and they require very complex soil structure interaction. So depending on the material and type of structure you use, you can have quite different analysis requirements. Then you have the component design, and in most codes, it's covered by some sort of demand and capacity calculation, be it through forces or stresses. Once you calculate your loads and you analyze the forces that are actually acting on the structure, you also need to make sure that you have the resistance, and both the loads and resistances are uncertain. And what the codes give you is the probability of a given load occurring and a probability of a resistance occurring. And they define safe bounds at which the resistances, exceed the loads. And that's really what engineers' job is about, is to make sure that the resistances are more than the loads, among other things. But that's really our job, to make sure that it stands up and there's enough conservatism in the design that it's a reliable and robust structure. Again, you can do it with pencil calcs, Excel software. It doesn't really matter. I think the most important thing here is to really understand how the structure works and how to calculate the capacities. It's the principles rather than the specific method. And then once you've developed your design, you go into detailing. And again, a lot of different structures require different detailing levels. For example, for reinforced concrete structures, you have lots of bars to design. You have a lot of detailing and reinforcement. For PT anchorages and PT arrangement, quite complex bit of design. You need to make sure that the forces are transferred correctly and they are going in the right direction. For steel, you tend to go for welds and local stiffening. That's a lot of detail in that. So you tend to go and design that once you have a concept. Bolts and connections for steel and composite structures. And in all bridges, there's a huge amount of smaller items such as manhole covers and lighting fixings and barriers. And then once you've covered all of the details and you've really designed all your structure, then you have to deliver it somehow and communicate it to your client, communicate it to your contractor, communicate it to the public. And nowadays, simple 3D modeling or BIM modeling, which also, as well as 3D information, includes some information about the items that you're designing. So this is increasingly the way to go. But the drawings are still strong, and people are still using drawings and are used to using drawings. I think that's more of a history and a culture, but that hasn't gone anywhere. And a good engineering drawing is always valued. And obviously, then you have schedules and quantities and calculations that you deliver at the end of your design. So to recap, we've talked about selecting the initial shape of the bridge, and we've talked about the design development loop and the iterations of load, analysis, component design. We talked about the detailing and delivery. And we have discussed the use of manual and computer-aided methods, and we sort of established that it's more the principle than the method that's important. To get it a little bit more visual, and I guess to consolidate it, I came up with a simple case study. It's similar to a project I worked on. Unfortunately, I cannot share the details of the actual project, but it's very, very similar to something that I've designed. And this is something that you would be looking in your professional life if you become a bridge engineer. So you tend to get some sort of requirements. In this case, you have a canal that you want to cross, and you have an existing footpath on both sides that needs to remain there and needs to remain accessible. The client was building a very big residential development on this side, and some recreational area here, and a new boating marina in this side. And they wanted to really connect the two sites together. So they approached our company, and they asked whether we can design something. So this is just to show what the marina would look like at the end. So what we had to do is, first of all, we needed to understand what the client really needs, where everything is. We developed some drawings, 3D models, surveys, analyzed that information to understand the constraint. We looked at the requirements. For example, the canal needs to be navigable, so the boats must go underneath. You must also make sure that the cyclists and pedestrians are comfortable walking underneath the bridge and on top of the bridge. You need to make sure that the bridge is accessible for people in wheelchairs. There's also a requirement for horses because it's an equestrian site. So we had to consider quite a few different requirements, and we came up with this orange envelope. We then looked at a few alignments because it's an unusual site. You're not really crossing from A to B. You're crossing from A to B, from A to C, from C to B, and vice versa. So you really have 3 points to connect here. So it's an unusual site. And we looked at different alignments, such as this sort of curved banana-shaped bridge. We looked at actually separating it into two bridges, but at the end we came up with the three-legged kind of Y-shaped wishbone structure, which is quite interesting. We then came, because of the shallow requirements, we went for the steel box girder, and steel boxes are quite efficient. And so when you have a tight constraint, especially for pedestrian bridge, that was good. We also had a good relationship with the steel fabricator, and that really drove the design of the structure. And again, the design loop. So we had this concept design. We had this shape that we thought was perfect for the site. Then you do the analysis, where you determine the loading, which is I'm not going to cover all of the design process, but let's say this is just a bending moment diagram with your critical moment. You calculate this deck section you don't have to follow the numbers, but it's just to show you what sort of work you will be doing as a structural engineer. You calculate the stiffness of the structure, the I value, your segment area. You calculate the elastic moduli, and considering the strengths of the material that you specify, you calculate the resistance moment in here, and then you compare your load with your resistance, and you hope that it's okay. If not, then you change your shape, and you go through the design loop again. So that's really your life and your work as a structural engineer. There's a lot of other checks, like there's plenty more shear calculations, vibrations, all sorts. And this was quite simple. We had a stick model for it in FE with different sections. But for the center bit, where it was quite complex, and we decided to go with a full sort of 3D shell model for the analysis. So as I was saying, the choice of methods, it can be as simple as Excel calculation, it can be software, it can be very complex engineering. That's your job as engineer to decide what you trust. And then the delivery. You draw each span and you specify plate sizes to communicate that to the contractor. And this is not the bridge that I was talking about. I had to give you a different picture, but happy days, that's the happiest you ever be, where your bridge lands on site, everything is safe, you can stand, you can jump on it, and it's really, really satisfying to see the bridge built on site. So to recap, we talked about the site constraint and client preferences, how we decide different options, select the shape, and go through this design loop that we've discussed numerous times already. So what's happening in the bridge market at the moment? You start looking at longer spans. So this is the Çanakkale Bridge. It's going to be the next longest bridge in the world to be built in Turkey. So increasingly longer spans. So the obstacles that are shorter already been crossed. You're looking at obstacles that are much longer and that require much more engineering. Innovative methods of construction. So the delivery. So here, for example, it shows the use of a modular transporter to install the bridge. So instead of using a crane, you could be using these modular transporters. That's a very hot trend in engineering. Sustainable materials. These are absolutely beautiful bridges in Canada, built from timber. Very low embodied carbon in them, beautiful structures, very warm look as well. That's a very increasing trend. Digitalization. So I was talking about building information modeling, especially complex part like this, reinforcement detailing in 3D. This is for from Tekla. Health monitoring, health monitoring and looking at the structures. And then there's the future, and the future is quite interesting and bright. We see. You'd think that all of the engineering was invented, but no, there's a lot of new materials that are coming on, polymers, ultra high strength concretes, among others. You have a lot of research going in seismic and wind loading, which are quite uncertain and quite difficult to predict. So still, there's a lot of work in research. And if you're an academic type, there's plenty of research for you to do as a structural engineer. And in dynamics, understanding how the structures behave, not in a static way, but in dynamics. And you have even more exciting things like 3D printing and robotic fabrication. Like this bridge here is a bridge, I think it's an experimental bridge in Netherlands. It's a fully welded bridge. So you have this robotic arm that completely prints this bridge in metal. It's mind-blowing. And then you have the health monitoring. And looking after the existing structures is extremely important and has been a big business recently. Just making sure that the current monitoring and understanding the current structures, making sure that they're safe and they can continue past their design life is a very hot topic and very important one. Yeah, that's another picture of this amazing bridge, which was fully 3D printed. Just to conclude, there's various ways that you, as a student or as an early career professional, can contribute, and the industry is really subdivided in four ways. You could work for a client or an authority, which is mostly looking after the old structures, or you can be this initial step where you define structures, define the need for structure, look for where structures are needed. And you sort of work as a boss. You hire everyone else in the process and make sure that the design is delivered. You can work on the design side, which I personally work in, and I really enjoy, because you see the structure from concept and you make sure that you define it, you design it, and there's plenty of work in the design offices in India and around the world. You can also be an engineer on the construction side. The construction side is not only for builders, it's also a place for engineers, especially for bridge engineers, where it's not very straightforward on how the bridge is built. And so a lot of work is also needed on site to understand bridge behavior, to understand how to construct things safely. And there's plenty of work as well in operation of the bridges, especially old structures and even some of the modern structures. They require constant monitoring, constant operation, and constant input from engineers. In terms of the skill sets that you can consider, I guess I should probably have started with academic. You can go into academic, you can stay in university and keep developing the sort of keep leading the edge in terms of research. You could be a technical person. You could start as a graduate, as everyone really in stages really in this direction from left to right. You start with technical ability. Some people stay as technical directors. They go into senior level and in depth as technical directors and stay in the technical side. Some people prefer managing BIM and managing drawing production, which is a rewarding job because you see the deliverables coming out, and that's a great opportunity. So if you're a graduate, you can then start supervising the delivery. You can manage technicians. You can then move into project management, both in design, in client side, and construction operation. Project management is needed everywhere in all the industry, and you tend to go again from delivery to management of the whole project. And once you develop into a more senior person, then you tend to go into business development, looking for clients, looking for projects, making sure that your construction company or design company stays in business. Okay, so it's time to wrap up. And finally, I would just conclude this presentation by talking about what we've talked already. And we've covered a little bit of bridge philosophy and why we need bridges and importance of human consideration as well as hard engineering knowledge. We went to talk about bridges and talk how they compare with buildings. We talked about different project stages and design principles and design iteration. We've discussed current trends and the future that awaits us, and we've talked about how you as an engineer, as a young professional, can get involved. And I think there's quite a lot of excitement that's awaiting us in the future. Thank you very much. If you